Hello, everybody. Welcome to one more telecom seminar, which is hosted by Technology Innovation Institute in Abu Dhabi. So along the last months, we are running a series of telecom seminars, which have been delivered by renowned researchers and professors worldwide. And for today, it's a big pleasure to have Professor Lajos Hanzo from the University of Southampton in UK as the speaker of the seminar. Well, Professor Lajos Hanzo is very well known professor in our community. And indeed, he did some introduction. Actually, if I would read now his CV, I would definitely spend the whole day. But in order to just summarize some of his great achievements, let me introduce officially Professor Lajos Hanzo by reading a short version of his biography. Professor Lajos Hanzo is currently a Life Fellow of IEEE, and he received the master's degree in electronics in 1976 and his doctorate in 1983 from the Technical University of Budapest. Since 1986, he has been with the School of Electronics and Computer Science, University of Southampton in UK, where he holds the chair in telecommunications. He is currently a former member of the Hungarian Academy of Science, and he is the former editor-in-chief of the IEEE Press. He has served several terms as a board of governors of both IEEE Communication Society and Vehicle Technology Society. He has published more than 2,000 contributions at IEEE Explorer, 90 widely IEEE Press books, and has helped the fast-track career of around 123 PhD students. Over 40 of them are professors at various stages of their careers in academia, and many of them are leading scientists in the wireless industry. Professor Lajos Hanzo is an enthusiastic supporter of industrial and academic liaison, and he has offered a range of academic and industrial courses. He is also a fellow of the Royal Academy of Engineering, a fellow of IIT in AIDRC. He has an endless list of awards, and I think the last one, he was the recipient of a 2022 IEEE Eric Summerfield Award. Professor Lajos Hanzo, I'm confident most of you know very well, is a wide-band researcher. And along his career, he worked in different research topics, ranging from wireless communications to communication theory, signal processing, information theory, machine learning, artificial intelligence, and etc., with outstanding contributions in all of them. But in his talk, today's talk, he invites us to embark on a journey into the rich and wonderful world of quantum physics, where the sometimes strange new worlds of the quantum world will be discussed. So, Professor Lajos Hanzo, thank you once again for accepting our invitation. And we are very excited to join this journey. And now the floor is yours.
Well, thank you so much, Daniel. I think it can only go downhill from this moment onwards. You've been so generous in your introduction, and really warm welcome to you all. I think we can adopt a leisurely pace. In some little places, I might be galloping, but ultimately, my goal is really to enthuse you and kind of inspire you into looking into this, as you put it very eloquently, Daniel, weird and wonderful world. And I also want to prove to you that you don't have to be a quantum physicist in order to do this kind of research. And, you know, my hope is that you will see this by the end of the webinar. Perhaps you can also look at this little book, which was written by one of my friends, old friends in Budapest. And if you can read the title, it's got the subtitle, An Engineering Approach. So this is not a pure physicist approach, but it's an engineering approach. And as you quite rightly said, Daniel, it's a journey. So let's commence. Many, many thanks to the whole committee who invited me, and also to my valued friends back at base, as well as really fantastic to reunite with some of my old friends I spotted, Professor AIDRC, for example, online, and Yen Kai, who at some stage in his earlier career was at Southampton. So yeah, let's rock and roll, shall we? Okay, so for those of you who don't know where little Southampton is, so this is Southeast England, and I'm going to tell you about this journey through communications era version 1.0 to start with, okay? And so this is London, where I'm circling with my mouse. Hopefully you can see this. Of course, most of you have visited London, and we are just an hour on the train from London. This island is called the Isle of Wight, and at its western tip, there is a plaque which commemorates the first ever radio transmissions across the Atlantic carried out by Marconi. So he transmitted to Newfoundland. And so I could almost like say, wireless has a long history in Southampton. This is just 5 miles line of sight from where I am. And this is where Southampton Wireless lives. When Yankai was in Southampton, then we had an older building, but in 2005 we had a fire, and we are at the top floor now, again on top of the famous Optical Research Center. So this is the dream team with which I've been enjoying collaboration over the years. By now, they all went to industry, apart from Professor NG here down at the bottom, and Yuan Kao, who is currently in Nanjing. And ultimately, there are new collaborators and contributors as well, but they have been the most substantial collaborators in this project. So, bit of a historic preamble. I already alluded to Marconi here at the top right-hand corner. And as I said, this is a journey, so I have to really take you smoothly from James Clerk Maxwell, who laid down the foundations of electromagnetic propagation, through Marconi and Einstein in the 1920s, when he was awarded the Nobel Prize. By the way, it wasn't for relativity, interestingly, it was for explaining some optoelectronics properties. And then Claude Shannon, who is really the father of information theory. And now, here is the fantastic thing for this talk. When Daniel invited me to give this talk, the Nobel Prize was not given to these gentlemen. But just a few weeks ago, Alan Aspect, Anton Zeilinger, and John Clauser were given the Nobel Prize for their quantum-related research. And those of you who were at ICC in Paris would have heard the fiery keynote speech by Alan Aspect. It was extremely entertaining as well. So this is a real pleasure to really sort of introduce them to you if you haven't come across these gentlemen as yet. And so the journey continues, but I also have to say that I am an open-minded researcher. Maybe I should just call myself really a gray-haired student of our game, an eternal student. But, in engineering, there are always trade-offs. So we're going to have to really look at quantum communications with a pinch of salt and, follow the wise Chinese yin-yang philosophy. And so this takes me back. Now, we started from James Clerk Maxwell. Now we're looking at Gordon Moore in 1965. And really, this is when we are kind of entering the quantum era on the wings of Moore's law, because you can see here that back in 1965, Moore was really tasked with hypothesizing as to how the semiconductor industry will evolve and develop. And over the years, Moore's law remained valid. Every 18 months, the integration density kind of doubled, of course, provided that somebody was pouring the billions into the semiconductor industry, right? But we reached this stage, this kind of fuzzy region when integration density really has reached 3 nanometer. And so we have to deal with the quantum effects unless we want to make the chips bigger, but then they start breaking up and the yield goes down. So again, this would be an interesting after dinner talk, but here today I want to inspire you a little further and continue our journeys now throughout the wireless generations. And so you see here, I've got the 6G book in front of me, and that's what most of you are researching these days, probably along with my team as well. And so over the 5 generations, we arrived here at this fantastic smartphone. Believe it or not, I did an internet search, and in the current era, you can find a smartphone in India for about $10. However, and anecdotally, I just mentioned this because the most expensive one you find is about 10 million US dollars because it's dotted with diamonds. So it's more like a fashion accessory. So again, Daniel mentioned it's a journey, and the journey needs a map, right? And I'm now focusing a little more onto the past sort of 2 decades rather than the 200 years or so where I started out from. And I don't have the time today. And anyway, you know the story, so we will just focus on the quantum avenue here, as you see the top right corner where I'm circling with my mouse. And I leave Next Generation Parkway for another talk for some of you who are regular participating in this seminar series. So yeah, almost done with the historic preamble. And I do have a classic outline, as you see here, but it's a little boring really to look at a whole block of text. So what we're going to do now is really just highlight very briefly the quantum basics. I must admit, I will be glossing over lots of things because again, my main motivation is to show you this wonderfully open research field. So rather than doing incremental research, we're going to be doing frontier research, sort of really totally new things. But the nice thing is that we can actually really use our classical knowledge as the springboard for quantum communications. And so we're going to look at, like we usually do, the channels, the channel properties are absolutely vital for designing good systems, right? That's where everything is centered. And then we, just like in the classical world, we have classical codes. Literally every wireless system has got codes to mitigate the errors. And in the quantum world, what we need is quantum codes. And we will just allude to these, allude to the capacity of quantum systems a little bit, which is also wide open, and then talk a little bit about encryptions, quantum key distribution, the employment of quantum search algorithms as and when fault tolerant quantum computing has become a commercial reality. And finally, we conclude with some future issues. And this is really what I think the future is holding for us, which we have to explore jointly. But this almost utopian vision really says that, okay, we've got the terrestrial systems, and many of you are probably researching these famous space air ground integrated networks. So in order to cover the large coverage holes in the oceans and seas and, sort of sparsely populated areas of the globe like deserts and Siberia and so on. We need satellites, and we also need security. So one of the main justifications for using quantum communications is the ultimate security, right? So we will touch upon this as we go along. And I also want to mention that really in the space and ground integrated network context, the planes and drones and sky platforms, etc., also play an important role. Sometimes as relays, sometimes as actual base stations. So yeah, this is the vision, and we will return to this picture at the very end in a bit more detail. So if you haven't really been exposed to quantum computing, you might wonder, well, what on earth is quantum computing? I have nothing to do with this. Well, I show you that there's a huge, big global momentum, and this picture, which talks about 5 billion euros funding, is only really for the European Union. Because the Science Commissioner promised this amount of funding, and there are very large-scale European projects. But President Biden also announced very recently a program. And if you are in China, again, the quantum science has become part of the next 5-year plan. So the Chinese government is also pouring lots of money into this. Not long before Daniel hopefully manages to get a bit of funding in Abu Dhabi and other parts of the world. So again, in the UK, just because I know this very clearly, that the government has invested about 600 million pounds over a period of 6 years. So yeah, funding is of course the fuel of research, right? And we are again on a journey, so we have to get on with the journey. So looking back for a moment again with this historic perspective we are projecting, T.J. Watson famously said at some stage, but I'm also quoting it a little bit out of context just to make a point boldly and explicitly. I think there's a world market maybe for 5 computers, right? And of course, we have now many more than 5 quantum computers, but this gives me a chance to just really look at when it all started. And so this is now, rather than looking at the classical history, looking at the quantum history. And so you see here the famous British scientist Richard Feynman, who was a physicist, really proposed a framework for simulating the evolution of quantum systems, such as a quantum computer. And he also had this incredible revolutionary idea that we could actually map the information to be transmitted onto the spin of an electron, for example, or the charge, rather than having to map it to 0 volts and 5 volts. And everything kind of evolved from there. So a lot of people got excited, especially during the 1990s. In the 80s, developments were relatively slow. And all I have time for today is really just to show you the density of innovation rather than take you through all the innovations in great detail. But a very significant point I wanted to make is, Peter Shor's algorithm, where he was able to factor an integer into its prime factors at a very, very low complexity. And this, of course, was the beginning of very important research activities in ciphering and cryptography, because much of the cryptographic systems rely on challenging, difficult mathematical problems which cannot be solved easily by classical computers. But the quantum computer is a real threat. So there's a whole bunch of research activities on post-quantum cryptography. And in this context, of course, grew physical layer security, for example. Yes, so then Grover's algorithm and the Boyer-Brassard-Hoyer-Tapp search algorithm, as well as the Dürr-Hoyer algorithm from 96, are very, very important. So suppose, if there's 1 million telephone numbers in Abu Dhabi and I want to find Daniel's telephone number, I would have to look through 1 million entries. But if I had a quantum computer, then based on Durhoy's algorithm, it's actually sufficient to search on the order of square root n entries and find the telephone number I'm looking for with a near unity probability. So yeah, this is a huge invention, of course. And just to really sort of list a few of our modest contributions in the past kind of decade or so, we then developed all sorts of algorithms for solving large-scale classical problems. So observe again, large-scale classical problems, right? So what can we do as and when these computers are commercial reality and how far we can go? And so, of course, this is a bit reminiscent of what we do, like Yen Kai in his research, for example, used genetic algorithm-based multi-user detectors. And, you know, those were capable of approaching the maximum likelihood solution at a fraction of its complexity. And that's really what these quantum algorithms can do as well. So anyway, um, almost finished with history in our journey, but this is the sort of first computers in Manchester. It's called the Manchester computer. It's a large, greasy piece of hardware. You remember, this is what IBM teacher Watson said, and really this was one of the manifestations of this. And then look what we ended up with. It's totally incredible because there's gigaflops capabilities in these laptops at commercially affordable prices of a few $100 or euros or pounds. And by the same token, you know, the smartphone is another amazing manifestation of this. In fact, it has more computing power than most laptops, but it's specific. So you could actually argue that the smartphone is a special purpose computer, just like the quantum computer is a special purpose computer. Actually, it's dangerous to make such predictions, but I will say this again, that it's unlikely that quantum computers will be able to beat classical computers in solving all problems. It's totally unlikely. However, they will beat them in many specialized tasks. So, you know, therefore, there will be probably a hybrid era. And this is the 17 qubit IBM quantum computer. So perhaps you get my point. You know, this is where we were 70 years ago in the classical computing era. And this is where we are today in the quantum computing era. And that's the 100 qubit quantum computer. So just to mention a few sort of trends in this context. In the current era, as you see, we only have like 100 qubits, although the largest quantum computer on planet Earth is today the D-Wave computer, which operates on the basis of 2048 qubits, but it's not it's not a typical quantum computer. It's called an adiabatic computer. And so the main categories are, the fault-tolerant large-scale quantum computers of the future. And in the current era, we call them near-term intermediate scale quantum computers. So what we do is we try to build larger computing systems with the aid of these so-called NISQ computers. And so we have to use quantum codes, for example, in very low rate, very powerful quantum codes in order to ensure that their computations are protected against the deleterious effects of decoherence. So this is the Intel chip, and there's really many different technologies. Just wanted to mention that obviously there's a lot of uh, wrangling, if you like, in the scientific community as to which particular technology is the best for implementing quantum computing in general. So there is a race currently amongst the different philosophies, and only time will tell us which is the best one. But later on, we will talk about the what is called the fidelity or the reliability of quantum computers a little bit. So in contrast to serial computing, where we solve a problem by, substituting each possible, candidate solutions into the computer, like in a maximum likelihood search, we can think of it as, again, in the lab, we have a large cluster of Linux computers, maybe 50 of them. And so you can distribute the tasks to everybody's computer, but it takes a lot of time and effort in order to distribute them, in order to find the answer. And in quantum computing, with the aid of the quantum parallelism, which I will highlight as we go along, this can be done much more efficiently. If you think about this phenomenon, in everyday terms, it would be almost like I was able to shake there's 45 people online, I can see everybody's hand simultaneously. I would need 45 hands, right? So I'm just sort of jokingly using these, everyday analogies. And as I mentioned, fuel of research is, of course, funding, but also having a body which is really supporting it. And if you are an IEEE member, then you would probably have heard that there's an IEEE Quantum Initiative, a very vigorous one constituted by about 8 different societies, and the Communication Society as well as the Signal Processing Society are part of this initiative. We meet every Monday and discuss the way forward, both scientifically as well as in terms of management of the program. And I already mentioned Joe Biden's, President Biden's new initiative is pouring funding into NSF in order to, sort of progress the quantum science ideas. And finally, closer to home, again, if you are a ComSoc member, I hope you are, then I would like to invite you to join our ComSoc initiative, which is the Quantum Communications and Information Technology Emerging Technical Subcommittee. This committee has now probably over 500 members. But at the moment, I can see that there is a huge demand and need for tutorial material and a kind of discussion where we, as a community, educate each other. And so we started this now, over 5 years ago, and it's running quite successfully. We have just now an upcoming meeting. So at GlobeCom and ICC, we always have a committee meeting, and we have tutorials by renowned speakers, etc. So yeah, please send me an email if you're interested in joining, and I will help you with that. But you can actually just simply put into Google's QCIT, and you can log on at the website to join. Okay, so now a little bit of introduction to quantum technologies. And no doubt you have heard of Schrödinger's cat, probably the most famous cat in the world. And because this is a bit of a cruel story to illustrate superposition, so I'd rather probably use another one, which again is a bit of an anecdotal thing, but let me just illustrate for you. Here is a little coin, a £1 coin, which I put in this cup, and I sort of rattle the cup, and really I don't know whether the coin will be head or tail when I lift my hand or the cover of the cup. So you could think of quantum computations as the quantum bits being in an equiprobable superposition of logical ones and zeros. And we have to carry out all the computations while I'm rattling this coin. In other words, while the information is in the quantum domain in the superposition of logical ones and zeros. Of course, this is a single bit computer, right? We need many, many qubits. And so that's what the community is working on. But, a more scientific kind of explanation perhaps is imagine that we have an atom here and with an electron orbiting around the nucleus, and there is really two legitimate energy levels, these solid orbits, as and when we observe or measure the electron's energy status, energy level. But in a three-dimensional picture, it looks more like this. So again, we don't know whether it's a logical 1 or a logical 0. But when we observe it, and the physicists use the word measurement, of course, in engineering, in electrical engineering, we need a measuring equipment. But observation means that you observed it like I did observe the coin, and then it falls back into the classical domain. So effectively, you cannot manipulate it anymore in the quantum domain, right? So obviously, that's just a very simple kind of explanation. And this is the so-called Bloch sphere, where we try to visualize the quantum states representing the classical domain information in the quantum domain. So we have a logical 0, and this chevron-like, this triangular-like kind of sign at the right is the so-called cat operator, which comes from the word bracket, and the logical 0 and logical 1 are at the north and south pole. And because this is a complex number which can assume arbitrary values on the sphere in the three-dimensional space, so all the so-called pure quantum states are on this Bloch sphere. And as and when, for example, decoherence attenuates the amplitude or imposes some phase distortion, even phase flips possibly, then we end up with non-pure states. And so a little more about the quantum physics side of things. Probably that's all what we talk about quantum physics in today's webinar, but very briefly, we mentioned already the superposition. And so we write down the superposition of a logical 1 and a logical 0, as you see here at the left-hand side. And we have these amplitudes A1 and A2. And the constraint is, of course, that all probabilities must add up to unity, of course. And so when we carry out a measurement or observation, then the superposition falls back into the classical domain. The next one is the so-called no cloning theorem, which is again vitally important. And the reason we mustn't clone a quantum bit as such, we mustn't touch the quantum bit, because then again it falls back into the classical domain. And indeed, this is why the quantum systems are so secure, because if the eavesdropper is perturbing the quantum state, then we can observe that, we can notice that rather, and then we can start the session again to avoid eavesdropping. So the bottom line is, however, that this no cloning theorem doesn't allow us to use, for example, copying of bits. So we cannot use, for example, say repetition coding in the quantum domain. We have to use so-called unitary operations which manipulate the information on this Bloch sphere from one position to another. And so a little more again as we go along about this, but the final one which we need for our discussions is the so-called entanglement. So what is this mysterious entanglement, which of course, again, this year's Nobel Prize winners studied in great detail. And this really means that if, for example, the spin of an electron is changed here at Southampton, almost not almost instantly, it changes in Istanbul, where Erdal Panayırtı is sitting, for example, or in Singapore, where Yenkai is sitting, or in Abu Dhabi, right? You say, this is science fiction, right? But in actual fact, I must emphasize that at the current state of the art, nobody was able to demonstrate this unless they used classical domain preparatory operations, which of course has to obey the speed of light. So we cannot claim that quantum communications provably violates the speed of light. It doesn't mean that. And indeed, this little schematic, which is from this paper down at the bottom in transactional communications, really looks at the quantitative issues of entanglement, and also how we can mitigate realistic entanglement, realistic kind of noisy or a decoherence impaired entanglement in direct quantum communications. And so in this context, you see here that there's a classical channel, and so we have a transmitter. We map the information to what is called the Einstein-Rosenstein, um, Einstein-Podolsky-Rosenstein pairs. And these pairs are entangled with each other between the transmitter and receiver. And so this is the essence of quantum teleportation and quantum communications. Interestingly, in most people's minds, quantum communications today is more like quantum key distribution, but that is really only a key negotiation operation. And so this is why I emphasize here again the direct quantum communications, which means true communications of information, the desired information, not only the quantum keys. But this is the most famous experiment in which really quantum key distribution was demonstrated in China. Scientists from the University of Science and Technology China in Hefei really demonstrated this. They beamed up the quantum key and then beamed down from the satellite 1,200 kilometers away. And this is a very, very substantial achievement for many, many reasons. Even free space optical in this context is a challenge to realize, and we chat about this in a minute. Some of you might have done actually work on free space optical using laser communications. But the issue is that at the current state of the art, there is no long-term quantum memory. And hence, we have to deal or conceive or deal with basically single photon memory solutions. This is only a bit like the near-term intermediate scale quantum computers. It's a temporary solution to avoid having to store the quantum information because it's contaminated by the quantum decoherence owing to its very low power, right? So the low power means that the eavesdropper doesn't have easy access to it, but we also have to deal with the complications of this low power. And again, this kind of greasy large-scale satellite hardware might remind you of what I said about these old classical computers. So we sort of anecdotally spoke about the current quantum computers, and this is the current QKD system over satellites. Over optical fiber, it's already a commercial reality. And a little more about this in this slide. Cheers, just to really give you a moment to gather your thoughts. So the longest fiber-based quantum network, as far as I know, is between Vladivostok in Siberia and Helsinki in Finland, going through much of Russia. I don't know, my hope is it hasn't been destroyed in the war, through Moscow, St. Petersburg, and Helsinki. So it's about 15,100 kilometers. But of course, this really entails relaying, and you see here these nodes indicate, the relays. But these relays are extremely sophisticated and expensive to build. More about relaying as we go along, but we know as a community quite a lot about relaying in the context of amplify forward and decode and forward relaying as such. And so, these lessons can be deployed in the quantum world as well. So this was well, we started out from the satellite channels, right? A little bit on the fiber channels, and now a little more again on the free space optical quantum channels, which is essential enabling technology for quantum communications over satellites. And many of you know a lot about this. If the subject is interesting to you, based on the free space optical technology, please visit my website. I actually sent a link to Daniel where I prepared a whole bunch of tutorial papers for you, including this paper as well. And so you would find obviously a lot more detail. Here I'm glossing over a lot of things, but one of the hostile phenomena we have to deal with is the beam wandering in free space optical channels. And probably this is the best moment for me to mention that just like in the classical world, we typically have the Gaussian channel, which is essentially modeling the Brownian motion of electrons in the receiver. So if I buy a more expensive, a better receiver, then the noise figure will be lower, there will be less noise, and we can receive, lower power signals. Then we have the fading channel, which could be fast fading, could be shadow fading, which is slowly moving, etc. And to a degree, this beam wandering, the FSO channel I'm talking about, is reminiscent of the true transmission channel. And when I come to decoherence, that will be reminiscent of the Gaussian channel. So every piece of quantum hardware is subject to decoherence. And just like we can't get rid of the Gaussian noise, we can reduce it, but can't get rid of it. Similarly, the decoherence will always be there. So even over a computing system where no transmission takes place, we will need quantum codes to mitigate it. And that's the uplink. You see that the laser signal goes through the atmosphere and it's subjected to turbulence-induced spreading. And at the satellite, we can't have really a large receiver aperture. So, that really degrades the performance quite substantially. And the same is true for the downlink, although on the Earth, we can have a much larger receive antenna, so the situation is a bit better. A bit reminiscent again in the classical world, we can do a lot more things at the base station than at the UE, for example, the handset, right? So yeah, this paper again discusses these things in great detail, but let's just really sort of pause for a moment and turn to uh, Dr. Einstein and ask him, how do we deal with these hostile phenomena? And of course, jokingly, he might say, well, just make sure, young man, Lajos, eliminate the quantum flips, right? And then I might really hasten to ask, so how do we do that, Dr. Einstein? And so he would say, well, obviously it would depend on the quantum channel and depends on your hardware and depends on whether it's fiber or satellite channels, for example. So let's talk about these now a little bit. We mentioned some of the transmission channels here, right? Now we're going to mention the sort of processing channels reminiscent of the Gaussian phenomena. And we will be looking at just one particular gate. which is based on the semiconductor implementation of quantum systems, and it's called the controlled NOT gate. And the controlled NOT gate essentially is a 2-qubit gate. There are, of course, more sophisticated gates which handle more than 2 bits. And this is reminiscent a little bit again of the classical domain. We have the AND gates, the NOR gates, we've got the inverters, right? So the inverter is a single bit gate, AND gates and NOR gates are, 2-qubit gates. And so if you look at this little list, as I said, there's a bit of a competition ongoing across the globe. And the best one here at the bottom seems to be the University of New South Wales Technology and Keio University in Japan, and New South Wales in Sydney. They managed to achieve a fidelity of 99%, but 99.59%. And so the physics community, where all the quantum research started, they tend to use this fidelity as opposed to the bit error ratio, but it's really just 1 minus. So it's fairly simple. Right, so let's see, this is the channel, but the channel is not well modeled, not well understood, because there's so many implementations, and it depends on those implementations. So this is a bit of a classification tree, and I have to sort of speed up a little bit because I know that the end of the hour is approaching. So I mentioned this environmental decoherence, which is really owing to lighting and the decoherence in the circuitry itself. And there's 2 very simple models, the amplitude damping and the phase damping, which are typically related to photon emission. If you emit a photon, you lose some energy, right? And photon scattering is really reminiscent of phase damping. And then there's the so-called Pauli channel, which is really a sort of digital channel model. And I will now relate this to what is called the binary symmetric channel of the classical communications community. Because we now have these qubits, quantum bits, which are subject to both bit flip as well as phase flip, or in fact both. And there is this famous depolarizing channel, which is described in the tutorial paper in your pack that I sent to Daniel, and he distributed it. And so, the way you deal with this is, again, I just focus on the Pauli channel here at the top right corner, where quantum state really turns into remains unaffected with a probability of 1 minus p, where p is the total probability of decoherence induced errors. But the Pauli channel assumes that the probability of a bit flip, a phase flip, and both bit and phase flip is the same. And so, therefore, instead of p, they use, the community uses 1/3 p to represent the probability of each of these. Having said that, all of these technologies that we have here for the controlled NOT gate, for example, would have actually a sort of asymmetric behavior. So a word or two about the limits. We have the Shannonian capacity, and everybody must have passed exams in this community about it. You can't become a communications person without knowing the log base 2 1 plus SNR formula. But here we have the so-called hashing bound, which is the best achievable code rate that you can have whilst maintaining an infinitesimally low or even zero error probability. The red curve is an interesting one because it's related to what we discussed earlier on in the context of entanglement, namely that assuming that during instances of low teletraffic, you exchange some classical information, and then as a benefit, you would have, I find my way back here in a minute, you would have an improved maximum throughput. But you could almost argue this is a bit of a cheat because we communicated earlier, right? And so that is very true, but it's used in the community, the so-called entanglement-assisted hashing bound. And so designing codes that are capable of approaching this is really reminiscent of the task which the community carried out ever since Shannon set out the limits. And even though Bob Gallagher's LDPC codes could do this in the 60s, but it wasn't until the 1993 ICC paper by Claude Beroux that people realized that, yes, we can approach the capacity. And that is an open research problem. So if you are a coding guy, this is a challenge which would become an extremely famous invention if you could design these codes. So just to conclude on the channel side of things, so in the classical domain, as I mentioned, we can have cloning or copying, no problem. So we could have a third-rate code, for example, and we would have a binary symmetric channel, which allows us to corrupt the information of logical 0 into logical 1 with a probability of p and vice versa. And then at the receiver side, we just use majority logic decision. So if you have two zeros and a single one, then it's more likely that 0 was transmitted. In fact, you corrected 33% of errors, which is very substantial. But in the quantum domain, the typical model that we use is the so-called, it's like a quaternary system, because we have the no error scenario and then a third of probability for bit flips, phase flips, and both. So the coding design has to be, aiming for mitigating these and really approaching these limits. And this has not been achieved at the current in the current era. You could also actually almost immediately reflect that, oh, well, we know about finite block length information theory in the classical domain. Can we have the same in the quantum domain? And you realize that I'm now setting out huge challenges. If you are a PhD student and you love this area, love the challenges, start beavering away. And, really, we need every pair of hands to solve these problems under communications version 2.0. Now, I won't have time to take you through all these fine details concerning quantum gates, but these are the simplest quantum gates that we already alluded to, at least. And so these are the Pauli gates, where, effectively identity operation, just really remember, this is a unitary operation. So it's not copying, it's a unitary operation, which gives us effectively the same as the input was. And then the bit flip, the phase flip, and both the bit and phase flips are represented by these little matrices. And this is the control gate that I alluded to, which is basically, if you have a control bit that is 0, then it acts like a Pauli gate. In other words, it has no impact on the information. But if it has a logical 1, then it would act like a NOT gate, right? So it's a more sophisticated gate. Okay, so the last kind of set of issues I want to talk about perhaps today is cryptography and quantum key distribution. Before I do that, I almost forgot to show you. I already showed you this book if you are really probing further. But on the quantum coding side, there is this rather meaty book, and you can see that there are lots of solutions, but no ultimately emerging winner as such. And if the subject is in general of interest to you, I can also recommend this book, because it really introduces things based on linear algebra rather than introducing all the physics-oriented mathematics. Right, so on to the final issue of quantum cryptography, it's widely recognized that in the classical domain, we have the plain text, and then we have a key server. A key server gives us a secret key, and then we just take the modulo 2 addition of the plain text with the secret key. And so the key distribution channel is, of course, vulnerable. And if somebody steals the key, then they can decipher our information. And if you want to look at really quantum key distribution, the only difference is that the key negotiation is carried out in the secure quantum domain. So in this case, instead of having really 2 channels, we actually have 3 channels in quantum key distribution systems. But you don't necessarily have to think of 3 pieces of wire, for example, because you could have an optical fiber and use wavelength division multiplexing for accommodating all these. Now, the third one here at the bottom is that famous quantum secure direct communications sort of solution that I mentioned to you briefly. And these 2 papers here at the bottom, they give you insights on this. And ultimately, this is a very promising area to look into if you want to deal with quantum communications. And you can, of course, use it for just sending the quantum keys, but you can also use for sending the quantum information. So there's a lot of research now on this issue, and we've got this very new paper at the bottom, which just came out a month or 2 ago, and it really portrays the evolution of the global picture. The very first QKD experiments in the lab were carried out in the UK in '97, so that's really a quarter of a century ago. But then the developments sped up, expedited right across the globe, and China probably has the most quantum key distribution networks today in operation. So what kind of networks are these? And again, just a glimpse before I conclude, that we could classify the QKD networks into 4 types, relaying, or 4 types of relays, namely the so-called optical systems, where you use optical splitters and optical switches, and that is the most widespread and the current state of the art. So these are indicated in this slide with this side here, optical splitter. And then we have the so-called trusted relays. You see this modulo 2 like sign with a plus in it. And these really indicate that these are the ones here in the middle, for example. These indicate that the relay must be in a place where the eavesdropper doesn't have access to it. In other words, basically, it has to be in almost like a military base or a secure place. The next stage is the development of untrusted relays. And this is here, for example, where I'm circling with my mouse. The untrusted relays are so securely designed by protocol design that even if the eavesdropper has direct access to it, they cannot steal the confidential information. And then the final one is really the true quantum repeaters, indicated here at the left-hand side by these kind of wagon wheels, if you like. And so there's a sort of 10-year evolution or so in this slide, indicating what we need help with from you guys in the community. So very quickly, obviously, this is a point-to-point system so far, but we need networking, right, for quantum networks, for the quantum internet. And so in this context, really, we have something reminiscent of the 7-layer OSI architecture, but people are thinking currently in terms of more simple silos architectures. And so I will just show you the operation of a 3-layer system with the infrastructure layer, the control and management layer, and the application layer. These are described again in our tutorial paper, which is in the pack of papers. And so let's see, for example, Daniel and I would like this link to be a secure video link. So we would have to essentially contact the control and management layer so that we request secret keys. And then immediately the question comes back from the control and management layer, how many secret keys do you need? Is it enough for you to have just a single secret key for the whole of the hours-long webinar? Or do we want to replenish or change the secret key every 10 minutes? I have this little token with the university. We occasionally have to put in random numbers. And that is, a bit of a nuisance, but that's what gives us security. And so once this is sorted out, so immediately you can see that the limitation is really the secret key rate versus distance, because if we have an optical channel, for example, we mustn't amplify the signal. So there's 0.2 dBs per kilometer attenuation. And if you go far, then of course you're going to get more errors, right? So the handshake sorts this out, and we configure the QKD nodes. And finally, Daniel and I start the webinar on a secure link. Anyway, my time is gone. So just very briefly, the overall global picture, you remember I started out from here. And so we collected the state of the art in this single slide from this paper. You see the secret key rate versus the distance. So it's easy to provide, a high secret key rate for short distances, but not for long distances, right? And so the best one seems to be this asterisk, for example, here. By the way, these references are from this paper at the bottom. And so you have like 90-kilometer distance at something like maybe 3,000 keys per second, which is pretty good. And so it's hence commercially available. So I conclude with just a few things, for future research, although I highlighted many of these all the way through, but, the whole application scenario, we often talk about the verticals in the classical domain, right? What can 5G and 6G do for the verticals like transport and finance and banking and healthcare and government and, and so on, critical infrastructures. And the same is really true for the quantum communication scenarios, but the challenges are much more grave. We now are at a stage where we were in the 70s and 80s in wireless communications. So again, we need lots of pairs of hands. I mean, literally thousands of grad students who are interested in this and really play with the IBM quantum computer, which is, by the way, in open access in the cloud. And, we have to educate each other. Huge sets of trade-offs when we want to reach, that utopian vision when I started out with the space and ground integrated networks based on quantum rather than classical communications. So I haven't touched upon, trillions of issues, and, the story evolves. We continue the journey. These are just some of the trade-offs. Again, I will be actually giving a longer 3-4 hour seminar for ComSoc in November at some stage, where we delve into a bit more detail on these issues and trade-offs. But because my time is gone, thank you so much for staying with us so far. And I've got the time to answer any questions if this is of any interest to you folks. So maybe Daniel can check whether there's any messages in the chat and so on.
Thank you very much, Professor Lajos Hanzo, for this fantastic, very inspiring talk. It's up to stop here the journey. So we need to move it for the QA section. So So all attendees are encouraged to write the question in the chat box. Okay. So let me see. Yeah, we have one question from the participants. Why do secret key rates are so low in general?
Okay, yes. So the reason is really from a classical perspective. If the signal to noise ratio is low, we know that the transmission rate always is low. And we know that as the SNR improves, we can opt for, 16 QAM, 64 QAM, etc. So it's kind of plausible. We also know that the continuous input, continuous output channel capacity increases linearly, with the signal to noise ratio. But in the quantum domain, we are unable to amplify the signal. And therefore, we really have to deal with relatively short segments, especially at the current state of the art, where we have the optical signal subject to 0.2 dBs per kilometer attenuation, and we are not allowed to amplify it. So hopefully that kind of makes it plausible from a very simple perspective. But of course, future research will probably look at solutions where in the trusted relay era, we would be able to detect the quantum signal and then remodulate like we do in decode and forward relaying in the classical systems.
Okay. There is a comment in the chat box. Yes, all the seminars have been recorded. I will provide the link later in the chat box. Okay. And one question in another box is, do you recommend pursuing a career in quantum?
So do I recommend what?
To follow a career in quantum, to have a career in quantum.
I don't quite understand the word you say before quantum.
Yeah, I mean, do you recommend pursuing a career in quantum?
Oh, pursuing. Okay, yeah, got
Yeah,
you, got you. Yes,
yeah.
I definitely recommend it to you. Just to give you, a bit of insight, because I mentioned the IEEE Quantum Initiative, we also started a new conference, which is called the Quantum Week. And it was organized for the third time this year only. But the very interesting thing is that instead of, like, if you go to Globecom and ICC, 70% of the people are from academia and maybe 30% or even just 20 from industry. In this conference, it was exactly the other way around. So industry is unbelievably motivated. There's so many startups and so many jobs that all the people who worked with me as postdocs actually doubled their salaries when they went to industry. And I lost all the postdoc researchers because it's so hot. Okay.
Yes.
There was like 200 and something number of companies at the conference, and there was a huge amount of funding as well, which is again unusual. So I'm pretty sure it's hard, however, in the academia because we need, young, fresh talent to work with. And many of the PhD students would rather prefer just tweaking things a little bit, write paper 100,000 on a MIMO system, which are very well understood, whereas, quantum research is where nobody has all the answers, right?
Yes. Okay, another question. If you could have a very powerful quantum memory, what exactly they could make a difference?
Well, it would make a lot of difference because we could potentially just like think of caching, for example. What we do in caching is very often, store information in order we don't have to transmit it. And so in a way, that would be one thing, again, to benefit from. But there are other examples where we can circumvent a lot of extra computation by pre-computing things. And to give you an example, say, for example, if you have a simple BCH74 code, just as an example. So we have, 4 information bits and a total of 7 encoded bits. So you have 2 to the power 4, namely 16 legitimate code words, and you have 2 to the power 7 possible words. So we have to essentially find the words that are closest to one of the legitimate 16 code words. And we could just use a single memory in order to find the solution instead of calculating it. And calculations are a problem in the quantum domain because, again, the complexity is rather limited today. So we could very much benefit from having memory to circumvent and avoid computations.
Okay, I have a general question. In your opinion, what is the most astonishing property of quantum information that makes the world of quantum communication very exciting?
Okay, so let me make a first statement concerning my hunch. It's just a hunch, not a scientific inference. Quantum computing is at the current state of the art behind quantum communications, simply because the true quantum computers are limited in terms of the number of qubits. And so they heavily rely on really having sophisticated quantum codes. But quantum communications, as far as QKD is concerned, for example, is already a commercial reality. Anybody who has got the cash could go and buy a QKD box. You might argue, well, okay, so they could go and buy a computer from D-Wave, like, for example, NASA and Google and all the others have done. But the cost would be extraordinary. So only these kind of government organizations can afford it. But QKD is already a commercial reality, but very far from a widespread, sort of reality. And so it's innately secure and it's got a large headroom. And this is why I think if somebody is really interested in frontier research, where very few people know the answer, but of course, if somebody like a seasoned academic, say Erdal Panayirtsi would know, or you, Daniel, when the new PhD students come, they usually are frightened by new things and they would say, oh, but there are no papers for me to read. And that's exactly the point, because we have to write those papers, right?
Yes, exactly.
So there's that trade-off. But that was so wonderful about the team I worked with, because there was these 2 Greek students, for example, and they said, well, everything is new to us. We might as well look at this more challenging area.
Yes. Another question is, in your opinion, when quantum communications will be available globally?
I think it will probably evolve from this map, what we have. And so I think in the government circles in China is rather spread now for high security areas, but the length is limited. So because of the optical processing, it's typically metropolitan area networks, not large area networks as such. When it comes to large area networks, can be done, but then the repeaters have to be in secure places. And I can recommend probably 2 first readings for people depending on their interest. So if it comes to security, quantum security, then it would be this paper at the bottom, because it gives you a broad introduction with I think we had like 500 references. So it has all the references on this subject area. If somebody comes from the computer science area, maybe developing the quantum internet further. In other words, trying to, for
Yes.
example, look at how do we build a larger scale network with the aid of relying on communications as a black box, if you like. Um, and if you are perhaps a coding expert, because coding is so widely used in the classical domain, there is the so-called symplectic condition. It's nothing complicated really, but there is a condition under which every classical code would have its quantum domain equivalent. So I would encourage people to look into quantum coding, for example. So I sort of set out, 3, 4 different areas which are promising.
Yeah.
But the roadmap, how quickly it will become, more global, would very much depend on maybe these countries, to what degree they are willing to connect their network, um,
Yes.
because it's supposed to be secure. So actually, it should be okay to connect them. But of course, the
Yes.
whole reason people create these quantum networks is security. So we have to overcome these initial hesitation in connecting the
Yeah.
networks. And there's a lot of research needed on multiple access.
Yes, I agree. I'm not an expert in quantum communication, but from my knowledge, I think it's important to have this global network infrastructure. I mean, the quantum internet. I think after it's successfully deployed, we will assist many disruptive moments in our history, technology history. So, yes,
Absolutely,
yes,
absolutely. Like we can in the classical domain, we could almost say, all right, so uh, Elias invented the convolutional codes. Viterbi came up with the Viterbi algorithm. Then, there was the Bose-Chaudhry-Hockenham or BCH codes. There was the
yes,
Reed-Solomon codes. These are all people's names, right? Then
yes,
Ungerberg came up with the trellis-coded modulation in 79. Then, we had, I don't know, the turbo codes invented by Beru and his colleagues. So there are all these milestones which are all missing in the quantum domain, right? And we have to create
yes,
them. So if somebody wants to be famous, I highly recommend it.
yes, yes. We have another question from the participants. The question is, in usual physical layer security, we do not use any secret key. Is it the same way in quantum communications to implement physical layer security?
Okay, so that is a very interesting take. In a way, I think physical layer security could be viewed as as a consequence of post-quantum cryptography, because people were looking for other ways. First of all, classical cryptography operates at the higher layers, right? Not at the physical layer. And so there is a need for having some security at the physical layer as well, but also with the benefit of being capable of operating when quantum computers are more widespread. Uh, you could potentially argue that really QKD is something like a physical layer security technique, because although I haven't got that slide here, but there is a nice little slide in, let me find that paper. Is it? Yeah, it's in this paper at the top, where worked examples show you how QKD exactly works. And in very simple terms, Alice, the transmitter, would coin a secret key, but she would have to somehow agree with Bob what keys they would be using. And then she would map these keys to what is called rectilinear basis and diagonal basis in the quantum domain. And this is done in a random fashion. Bob also has a random set of rectilinear and diagonal bases. And Bob tries to receive Alice's quantum bits, but when he only gets literally just noise out of his receiver, then he would know that he applied the wrong basis. And so in a way, then they eventually agree about a key, but they also would drop some of the bits in order to further confuse the eavesdropper. And then they use classical error correction coding in the process of reconciliation. This is what they call it in quantum key distribution between the transmitter and receiver, when they reconcile their thinking of what the key is. And so if there is only one or two errors, because, for example, the eavesdropper tried to eavesdrop but didn't quite succeed in inferring the information, there may be just one error. So a BCH74 code can remove that single error. And so all this could be viewed as reminiscent of physical layer security, but it's not identical.
Okay. Another question is, what are the key advantages of direct quantum communication channel?
Yes, that's a very judicious question. So, as you probably by now realize, I quite like history, and the history of our science as well, not just general history of mankind. My father was a historian, so I always tried to learn lessons from history. And this paper by the famous Guilu Long, Professor Long of Tsinghua University, is about 20 years old. Uh, and the idea is that you don't just really use the quantum domain for the key negotiation, like in the middle figure here. You actually use it for integrated quantum communications. In other words, you don't have a need for having a separate quantum key. Everything occurs in the quantum domain securely. And so you could almost like draw a parallel where you might say, so in the QKD system, if the eavesdropper touches the qubits during the QKD negotiation, then the Alice and Bob would commence again from scratch. In the quantum secure direct communications, there's no separate key negotiation, only direct information communications. And hence, you, in a way, first of all, get rid of one of the channels in the middle illustration. So you only need two channels. And secondly, you don't waste capacity for the key negotiation, but you go straight for the information transmission. If you like, of course, again, you could use exactly the same principles as in QKD and only negotiate the keys. But why would you want to do that if you can have already direct information transfer? And so in the recent 2 years or so, QKD, no, not QKD, quantum secure direct communication developed very rapidly.
Okay, thank you. Any more questions? Yes, I'm not seeing any questions. So yeah, it's now almost 1 hour, 30 minutes of seminar. Maybe you are running out of time. And I'm going to conclude the seminar. Actually, first, I would like to thank very much Professor Lajos Hanzo for his time and for this fantastic talk. Actually, personally, I really enjoy the way you present and introduce the concepts. You make difficult things, you turn into easy to understand. concept. So I am one of your big fans in our community. And
thank you so much. You're too kind. You make me blush,
you.
Daniel.
Yeah, thank you very
I do
much.
think a lot about how to
Yeah,
present things, how to inspire people, because we
yes,
need more people in this field. So yeah, do join the QCIT committee, guys.
yes. Thank you very much, Professor Lajos Hanzo. Thank you all the attendees to attend one more telecom seminar. As I mentioned, this seminar has been recorded and it will be available very soon in TII YouTube channel. But I also typed a link where you can find all the previous seminars and the upcoming seminars. Okay, so feel free to disseminate the link with your colleagues and research collaborators, and hope to see everybody in our next telecom seminar. Thank
That's
you very much.
fantastic. Thank you again. If you don't mind, send me the link as well, Daniel. And I might
Sure,
see some of you in the longer version, in the November ComSoc seminar. So thank you so much. And
sure. I will send you.
yeah,
Thank
look
you very
forward to
much.
seeing you all.